Hello, my name is Henriquez, and today I'm going to present my second lab of Physics 2111 regarding the motion of a falling object. This is the table of contents and a brief rundown of this lab. Similar to the first lab, will be based on Newton's second law, but this time we will be applying the momentum principle as it's about non-constant velocity, so we recorded the motion of a falling object accelerating due to gravity. We use Tracker to observe and record the motion of the falling object. Then we use GlowScript to create two different computational models. And finally, the main goal of this lab is to compare both these two computational models we did with the actual observed motion. The main theory for this lab is Newton's second law. However, this time we will be evaluating motion at non-constant velocity. So the F net will be different than zero. The two main forces is the force of gravity acting on the object, which is the force between any two objects with mass. And for this experiment, we're using the acceleration of gravity at the surface of the Earth, which is 9.8 meters per second squared. We're also considering drag force, which is the force opposite to the force of gravity, caused by air resistance. And we will be experimenting with terminal velocity, the moment when the gravitational force is equal to the drag force. And for this experiment, the object is falling from rest. Here is the unedited clip I used for Tracker. We can see a tennis ball falling, and here we see the two main forces, which is the force of gravity and the drag force acting upon the opposite direction. So we see that the force of gravity in this moment in time is bigger than drag force as the ball is accelerating downwards. This is the edited version of the recording modeled by Tracker. So here we can see how Tracker identified each position of the ball at each instant of the motion. And here we can see the graph of the y values regarding time, so the y position of the ball regarding time. We can see how it went from position 0 at y to around minus 1.2. So it fell 1.2 meters during the 0.6 seconds of the motion. And we can see how the ball's position changed slowly at the beginning and then changed quickly at the end, meaning that the ball was accelerating downwards. Now shifting to GlowScript, this is my first computational model I did that is not considering the force of drag, only the force of gravity. Here in the code we can see the acceleration due to gravity, which is 9.8 meters per second squared. And then we have the interval of time of the motion, which is 0.6 seconds. And we see that the ball fell and it moved downwards in the minus y direction. And the position versus time graph, we see that the ball in this model actually fell 2 meters instead of 1.2 meters, so it fell considerably more than the actual model. In this graph, we can directly compare the model that is not considering drag with the actual observed motion, and we see that it fell considerably more and it accelerated more, as it's only taking into account the force of gravity and not the drag force. Here is the second computational model I did that is considering the drag force. The code we can see is very similar with the same time interval. However, I added the formula for the drag force, and I told the code that F net would be this time the sum of the force of gravity plus the drag force. And therefore we can see the motion in the same minus y direction. However, in the position versus time graph, we can see that the object is not accelerating as quickly, and we see a very similar graph to the one of the observed motion. Here in this graph we can see a clear view and a comparison between the three models: the observed model in blue, the GlowScript model with drag force in orange, and the other GlowScript model with no drag force. And we see that the GlowScript model with drag and the Tracker model are very similar. However, the GlowScript model that doesn't consider drag force accelerated way quicker, and this is because in real life air resistance exists and the drag force actually plays a part in the movement, so it's not only the gravitational force but also the drag force acting upon the object, and for these reasons these two models are very similar. Here we can see the three models regarding velocity versus time. The one with no drag force would just continue to accelerate throughout time, as there's nothing preventing this. The one with drag is more curved, as the drag force would continue to increase and would equal in terminal velocity to the gravitational force. And the observed model should look something similar to the second model. However, due to human error, it looks something like this. But we can see that the acceleration is starting curve down. It's starting to reach terminal velocity. In this time span, none are reaching terminal velocity, but the drag one and the observed model in a longer time interval would reach that terminal velocity that we're looking for. Now, to finish this lab, we'll look at a final hypothetical scenario, and it is, what if the object was thrown downwards instead of falling from rest? In this case, the initial velocity would not be equal to 0, meaning that the object would reach its terminal velocity in a shorter time period. And when it reached its terminal velocity, the F net would become 0, and the graph would level off at a constant velocity. Thank you, and I hope you really enjoyed this lab and learned a lot throughout the lab. Thank you.